Hey everyone, in this video we're going to learn how to graph piecewise-defined functions. To start, we're going to practice graphing a function on a restricted domain. So our first function is f of x equals 1/2 x minus 3, and the restricted domain is 0 is less than or equal to x, which is less than or equal to 8. So if we were to graph that linear function, we would do so by identifying the slope and a point on the line. So the slope is 1/2. A point on the line, because this is in slope-intercept form, is the y-intercept at 0, -3. Now normally we would plot this point, use the slope to get more points on the line, connect the points and draw some arrows. But here we're only graphing on the restricted domain, 0 is less than or equal to x, which is less than or equal to 8. Now that actually works out in our favor because the y-intercept is a perfect point to start at, 0, -3. Because that's when x equals 0. Now we can still use the slope, we're just going to stop when x equals 8. So up 1 to the right 2, up 1 to the right 2, up 1 to the right 2, up 1 to the right 2. Now we're at x equals 8, so we'll stop plotting points, and we'll connect only the points that we've plotted with a line segment. So there we have the graph of our function, f of x equals 1/2 x minus 3. On the restricted domain, 0 is less than or equal to x, which is less than or equal to 8. Now, if we wanted to, we could have created a table of values. And we would have started at 8. And we want to choose wisely because the slope is 1/2. So we want our inputs to be divisible by 2. So we could have said then 2, 4, 6, and 8. Gotten the y value of each corresponding x value, plotted the points that we got on our graph, and connected them. Now again, we don't want to put arrows at the end because that would indicate that the line continues infinitely and the domain would be all reals, where we only want the domain to be 0 is less than or equal to x, which is less than or equal to 8. So if we can understand this idea, then graphing a piecewise-defined function is just doing this multiple times. So we're going to take each piece of the function and graph it on the restricted domain. And if there's 2 or 3 or 4 pieces, we'll just break it down into smaller parts. So our first piecewise function, f of x equals 5 on the domain -6 is less than or equal to x, which is less than -2, and -3 on the domain x is greater than or equal to -2. Okay, so this first piece, we could think of it like we're graphing y equals 5 on the restricted domain, -6 is less than or equal to x, which is less than -2. So we've turned it into a problem, just like the previous slide. So I'm going to start by plotting the point -6, 5. I'll write that point out, right? That's going to be the leftmost point in this domain restriction. So -6, 1, 2, 3, 4, 5, solid point because we're equal to. And then the next point, right, we need 2 points to graph a line. Next point I'm going to graph is -2, 5. Now notice the reason the y value is always 5 is our equation is y equals 5. So -2, 1, 2, 3, 4, 5. Open point now, because we have to be paying attention, x can't be equal to -2. So we indicate that on our graph with an open point, and we're going to connect our 2 points with a horizontal line. Okay, so there's the first piece of this piecewise-defined function. 5 is the output, -6 less than or equal to x less than -2 is the domain. Next piece is y equals -3, and we're graphing it on the domain, x is greater than or equal to -2. Okay, so first point, -2, -3, right? The output's always -3. Now it's going to be a closed point because x is equal to -2. And we want more than 1 point to graph our line, so let's go -1. That's going to be -3. And we're going to continue plotting points where y equals -3 on the domain x is greater than or equal to -2. So that means we're going to continue that out, We can stop right about there, and we'll just put an arrow to indicate that that horizontal piece of the function is going to continue infinitely. Okay, something to pay attention to, x equals -2. Right? We are dealing with a function. Definition of a function is one input can only have one output. So we can't have two closed points here. So that's something to check when you're graphing. Maybe you weren't paying attention to the domain as closely as you should have. Okay, but we can check ourselves before we're finished with our graph. If this was a closed point, this was a closed point, wouldn't pass the vertical line test, right? Because one input would map to two outputs. So then we can go back to our function and see where we made our mistake. Which of those points should have been open. Okay, we could have created a table of values again the same way for that last slide. Okay, but 2 points is sufficient. Next up, f of x equals -1/3 x plus 2 on the domain x is less than or equal to 3, and x minus 7 on the domain x is greater than 3. Okay, so let's take this first piece. Okay, so that's like we're graphing the line y equals -1/3 x plus 2 on the domain x is less than or equal to 3. Okay, so here I'll do a table of values instead of writing out points, just so we can have a few different options. So the first x value, let's use x equals 3. So if we substitute 3 in, we have -1/3 times 3, which would be -1, plus 2 is +1. Now, next up in our table of values, we need an x value that's less than or equal to 3 that divides by 3 nicely. Well, let's go 0. Okay, when x equals 0, we have an output of 2, which is the y-intercept, right? This is in slope-intercept form. So we have 2 points, so we can graph those 2 points, 3, 1, close point, because it's equal to 3 on this domain, and 0, 2. Now if we want more points, we can use our slope, right? So just doing that, we're going to continue to the left, so we'll go up 1 to the left 3, up 1 to the left 3, okay, the reverse order for a slope of -1/3. Now I'm going to take my line, and we're going to go from this point through our points this way. And then we're going to graph the line y equals x minus 7 on the domain x is greater than 3. So again, table of values. So we'll start at x equals 3. So that's going to output -4. And then we'll graph 4. No reason to get any crazier than that. So if we plug in 4, our output's -3. So we'll plot the point 3, -4. That's going to be an open point because we don't have equality here. And then 4, -3, plot that point. And we can keep plotting a few more points using the fact that the slope is 1. And we will go from our open point that way. Okay, so here we have the graph of our piecewise-defined function. Okay, so again, all we're doing is graphing a single line, in this case, because they're both linear, a single line over the restricted domain. We do that twice, and the combination is our piecewise-defined function. Now, the reason I'm using the same color marker, even though I can go through many different colors, is to emphasize the fact that these two combined are the same function. I'm not graphing two separate things. Okay, these are just two separate pieces of the same function. Okay, and again, the emphasis there, especially at the point where the graph changes, okay, one should be a closed point, one should be an open point. They are functions, so they need to follow all the rules that a function should follow. Now, alternatively, instead of writing out your table of values, as you get proficient at this, we should be able to just take the x value in our domain, so in this case 3, plug this in, get the output of 1, so take the point 3, 1, and use the slope of negative 1/3 to graph, but just pay attention if we want to graph where x is greater than 3, or in this case, x is less than or equal to 3. So instead of graphing down to the right 3, we went in the other direction. But if you're unsure about that, plot 2 points, okay? We've talked about this before. We need at least 2 points to graph a line, so use that to make sure that we're defining the line correctly. Now we do have to make sure that that second x value is chosen in the restricted domain of that piece. Next up, f of x equals 4 on the domain x is less than or equal to negative 1, 2x on the domain negative 1 is less than x, which is less than 2, and negative 2/3 times x minus 2 plus 2 on the domain 2 is less than or equal to x, which is less than or equal to 8. Okay, so we have 3 pieces now for this piecewise defined function. So we'll start with 4. We're going to graph it on the restricted domain. X is less than or equal to negative 1. So we're graphing y equals 4 when x is less than or equal to negative 1. Okay, so let's do this without a table of values. So when x equals negative 1, y is 4. That's our first point. Negative 1, 1, 2, 3, 4. It's a closed point because we have equality. Now, x is less than or equal to negative 1. That's to the left. So to the left, the output's always 4. So that's going to be a horizontal line. So I'll draw a horizontal line going to the left. And we have our arrow. Next, we're graphing 2x on the domain. So we're graphing y equals 2x. On the domain negative 1 is less than x, which is less than 2. So let's start by finding the point when x equals negative 1. So when x equals negative 1, we substitute that in, and we get negative 2. So our first point would be negative 1, negative 2. And then when x equals 2, plug that into y equals 2x, y is 4. So we have 2 points. At negative 1, negative 2, that's going to be an open point. And at 2, 1, 2, 3, 4, that's going to be an open point. Now I'm going to use the line tool to connect these, just so I can make sure that it's perfect. So we're going to go from open point to open point with our line. Okay, so we've graphed the first 2 pieces. And last, we're going to graph y equals negative 2/3, x minus 2 plus 2. On the domain 2 is less than or equal to x, which is less than or equal to 8. Now we should notice this is very similar to point slope form. We could move the plus 2 to the other side, but we have 2x values, so we can just plug in and get 2 points on the line. So if we plug in x equals 2, we'd get 0 times negative 2/3, which is 0, plus 2, which is 2. So the point 2, 2. And then when x equals 8, plug 8 in, we'd get 8 minus 2, which is 6, times negative 2/3, we'd have negative 4, plus 2 is negative 2. Okay, so plotting the points at 2, 2, closed point because x is equal to 2, and at 8, negative 2, another closed point, using the line tool, connecting, we have that piece of our piecewise defined function. So we've graphed that part of the domain as well. Now notice, there's 3 pieces. There are 3 pieces in the function given to us. It passes the vertical line test, right? Particularly at x equals negative 1 and at x equals 2, right? There's only one closed point at each of those x values. And notice none of the pieces overlap otherwise. Okay, that's something to watch out for. We're still dealing with a function. Okay, so if you ever graph it and accidentally, maybe let's say this horizontal line, you graphed it going to the right instead of to the left. A good indicator that you've made a mistake is the fact that it wouldn't pass the vertical line test. Right? If this piece was pointed this way. Hey, sometimes what I encourage students to do is the first thing when they get their domain restrictions is break up the pieces, even just on the top of your graph. So negative 1 from -1 to 2, and from 2 to 8. And just inside each area should be only one piece of the function. Okay, so if you find that helpful, that's another tool you can use. Okay, just to visually see that you should have one piece in each region based on the restricted domain. Our next example, f of x equals -3x minus 9 on the domain x is less than -2, 1 on the domain x equals -2, and 1/2 x plus 4 on the domain -2 is less than x, which is less than or equal to 6. Okay, so our first piece, we're going to graph y equals -3x minus 9 on the domain x is less than -2. So let's find our starting point by using x equals -2. So when x equals -2, we substitute that into our equation. -3 times -2 is +6, minus 9 is -3. Now, instead of choosing another x value that's less than -2, which we've done before, let's try to use this point and the fact that the slope is -3. So we're going to plot the point -2, -3 with an open point because it's not equal to -2. Now normally, with a slope of -3, we'd go down 3 to the right 1. But the issue is that's at x equals -1. That's not less than -2. So instead of going to the right, we need to go to the left. So instead of going down, we'll go up 3 to the left 1, 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 and we'll connect our points with a line. And there's our first piece. Now, if you didn't fully wrap your head around using just one point and the slope, use a second point. Pick an x value that's less than -2. So -3, -4, -5, then you have your 2 points, and you can graph that piece of the function. Next piece, y equals 1 on the domain x equals -2. So this domain's not an inequality, it's just x equals -2. So when x equals -2, y is 1, and we have just a single point here. So -2, +1, there's our point. That's the second piece. There's no second point, there's no line, it's just a single point. And the last piece of our function, y equals 1/2 x plus 4, on the restricted domain, -2 is less than x, which is less than or equal to 6. So this restricted domain is bounded, right? It has endpoints. So when x equals -2, we substitute -2 in for x. We'd have 1/2 times -2, which is -1, plus 4 is 3. And then when x equals 6, substitute that in. We'd have 1/2 times 6, which is 3, plus 4, which is 7. So -2, up 1, 2, 3, open point. And then at 6, 7, so 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7 with a closed point because it can be equal to 6. Now make sure we're connecting the right 2 points. So we're going to go from the open point at -2, 3 to the point at 6, 7. And there we have the graph of our piecewise-defined function. Passes the vertical line test. In particular, if we look at x equals -2, if we drew a vertical line, it would only intersect at this point here because the other 2 points are open. We have 3 separate pieces. They don't overlap, right? Again, reemphasize, it passes the vertical line test, so we're good. Now let's go the other direction. Let's write the equation of the piecewise-defined function if they gave us the graph. Okay, so we have f of x equals, with our curly brackets, notice only one f of x, right? I'm not writing 2 separate equations. I'll have 2 separate pieces. Okay, so the first piece, we can write that in slope-intercept form because we know the y-intercept is 5. And we know the slope, if I look at the slope, we'd go up 2 to the right 1. Right, so the equation of this line would be y equals 2x plus 5. So I don't want y equals, Right, I have that f of x here, so I'm going to write 2x plus 5, and then I need to state the restricted domain that this is graphed on. So that's graphed when x is less than or equal to 0. I know equals because I have a closed point there. Now the second piece, so again we can write it in slope-intercept form because we have the y-intercept, and the slope, so -1, 3. Okay, so if I was to write the equation of just this piece, the equation would be y equals -1/3 x plus 3. So without the y equals, that piece is -1/3 x plus 3. And then we need to state the restricted domain. So that's graph from x equals 0 to x equals 6. But we don't include 0 because that's an open point. So 0 is less than x, which is less than or equal to 6. And there we have the equation of the piecewise-defined function that they graph for us. Last example. F of x equals. So now we're going to have 3 pieces. Okay, so first piece here, let's look. The slope, down 1 to the right 2, so the slope is -1/2. We don't have a nice y-intercept, but that's okay because we can use point-slope form. Right? We have a nice point at -5, 0. So the point-slope form, y minus 0 equals -1/2 times x plus 5. Well, the fact that it's y minus 0 is really to our advantage because that's just y equals -1/2 x plus 5. If it wasn't 0, so let's say we use this point just for comparison, we'd have y plus 1 equals -1/2 x plus 3. We'd just have to solve for y. Y equals -1/2 x plus 3 minus 1. And we can leave it in this form or we could distribute it out, whichever you prefer. But I'll use this original one that I got because it's nice and simple. So that first piece is -1/2 times x plus 5. Now I need to state the restricted domain. So let's graph from x equals -5 to -1. So -5 is less than or equal to x, which is, What I should notice is this point is technically on both pieces. So we have to make a choice. Do we want to include it in the first piece, or do we want to include it in the second piece? But we can only include it once. Again, get back to that function definition. Every input can only have one output. So I'm not going to include it in the first piece. Okay, now the second piece, if we're writing the equation of this line, the slope up to the right 1, so slope of 2, y-intercept is 0, so this is just the line y equals 2x. So second piece is 2x. On the domain, -1 is less than or equal to x because I didn't include it in the first domain, all the way to 3, less than or equal to 3. And then one more piece. This piece of the equation, that's just a horizontal line. That would be the equation y equals 5. So we put in just 5, right? We don't include the y equals. And that starts at 3 and continues infinitely, open point at 3, so the restricted domain of that piece is x is greater than 3. Okay, so a lot of detail goes into graphing a piecewise-defined function. It's almost like doing multiple problems in one example. Okay, and the same could be said writing the equation of a piecewise-defined function. Right? It's like we're writing the equation of multiple lines and tie it in with the restricted domain piece. Okay, so go through a couple graphs, go through a couple where you're writing the equation so you get comfortable with all of the little pieces. Right? And just to point out one last time, the equal sign here can't be on both domain restrictions. Definition of a function, every input has only one output. Okay, so you have to choose. If I put the equals here and not here, this would have also been correct. Hey, the choice is yours, but only include it once. And make sure you include it. Don't leave it out altogether, because that would be an issue as well. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.